Welcome to the afternoon session. Our first speaker is David Leung from IQC. Her talk is on the power of non-signaling and the PPT codes. Okay.
Thank you. Can you hear me in the back? Good. So thanks to the organizers for this opportunity for me to sell you a tool. I'm not selling you a lot of results. I'll show a couple of demonstrations what you can use this tool for towards the end of the talk. This is joint work with Will Matthews from the University of Cambridge. So following up on Graham Smith's talk from yesterday, we are concerned with communication using quantum channels. So to recap some of the most basic idea, a quantum channel basically takes some quantum state from the sender Alice and output it to some receiver Bob with potentially some change that represent the noise that happened during the transmission. Now, if you have more users of the channel, potentially you can perform, you can perform some error correcting code. Is the cursor sufficiently clear? Then I can save myself from having to hold the laser pointer. You can potentially perform error correcting code by encoding the data into a bigger Hilbert space with the hope that then you can detect for what errors may have occurred upon decoding and output a state that is more close to what it used to be than just sending it through the channel by itself. Now, clearly, if you want more redundancy, you will have to give up more space to send your data, and there's a natural trade-off between the rate, which I sometimes use the dimension of the message k, and sometimes I will take the log of it to represent the number of qubits you're sending, versus the fidelity that you achieve, which I label f throughout the talk. We assume that the number of channel is arbitrary, so it's a number of channel is n throughout. Now this question clearly is a very basic question about communication through quantum channel. There's nothing we can do to run away from it. And at the same time, it's just about as intractable as anything you can ever imagine. I'll give you one example that I was just talking about at lunch. Consider the amplitude damping channel that represents the excitation of a photon. Either you have a photon, you don't have a photon. You write down the channel. I still do not know after 19 years whether you can have a 3-qubit amplitude damping code that will correct for one error. I still do not know. So that's the status we're in. So we're trying to address this problem however way we can manage. We do not have a very good solution. You do not expect one. But let's see what we can manage within these constraints. Like, it's a difficult problem. So that's the problem we stated. We call it finite block length because we do not assume anything about the number of users n. Now, in one limit, it is quite familiar. The statement of the question become more familiar. So that's a limit when you allow asymptotically large number of users, requiring that the fidelity of transmission is close to 1. Then in that case, you only have one goal in mind. You maximize the size of the message to be sent. And that's, when you take the log of it, that's the number of qubits that you can send using the channel n times. When you divide by the number of channel users, then you get the optimal rate. We call the quantum capacity that you saw yesterday as well. So in that setting, you have an expression for how well you can do, thanks to Seth Lloyd, Peter Short, and Igor Davitek. These expressions, we use it in many, many places. They are extremely helpful to have around. With only one problem, that's in our way to understand the capacity. The limit of taking the number of users in the optimization is in principle unbounded. And there are plenty of examples in which we cannot take n equals to 1. There are examples in which we know that you can, if I give you n, you can find a channel that the expression with n there, you will see 0. But when you add 1 to that number, you will start to see a positive number. I have one of the authors sitting in here. So it is kind of a difficult situation to the point that the capacity of the depolarizing channel, which just send a qubit untouched with some probability, and sometimes replace it by the maximum mixed state, we do not know the capacity of this channel. We also do not know when the capacity is 0 in general. And for the channel I just mentioned, we do not know for some noise parameter whether the channel capacity is 0 or not. So that's roughly what we are at, even with this particular limit that we're taking, that the number of users is large and fidelity is 1. There are a lot of open problems here. So given the circumstances, what can we do? Now, it's a very pioneering thought back about 18 years ago that we can actually let some resources be free. and hopefully be able to understand at least some specific aspect of the communication problem in the hope to get something understandable. So that's what we got. If you allow entanglement for free, the quantum capacity expression becomes easy again. You essentially recover the classical result that you maximize some form of mutual information between the input and the output. For one use of the channel, everything is beautiful, is additive. That's 14 years ago when we found that out. Likewise, you can also allow something else for free. Like we're trying to communicate quantum data. So if you allow side classical channel in both directions, from sender to receiver and back, you can obtain a different result that the capacity in that case is equal to the capacity for the channel to create entanglement. But that capacity itself is unknown up until today. There's no expression. We do not know. We know something about the continuity, but we know sometimes it is positive, but otherwise we again know very little about it. So that's one idea that we hope to carry in this talk by giving some resources for free. That is, of course, it should not trivialize the problem. The assisting resource should be useless on its own. I mean, that's a baseline, what you're allowed to use. And it should simplify your problem to show insight on aspect of what you're trying to study. So that's the hope we are trying to achieve here with understanding the finite block length problem. So the resources we're looking at is this thing called the Nonsignalling and PPT Preserving Code that I will explain in the next 10 minutes. Essentially, we do not allow free entanglement. We do not allow free communication. We allow a little bit of each of these two things to be clarified later. And the reason we look at it is because it is mathematically trackable. It allows us to write down the probability of success as the value, the optimal value of a semidefinite program. For those who know what it is essentially something you can compute, and it has very nice analytic property that you can study. So we can show two examples of how to use this program to derive results. Some of them are analytical, and occasionally you will see that we do something funny. We study the finite block length problem, and we can infer a result in the asymptotic case as well. So sometimes it goes the other way around. And directly, we can also do numerical analysis that I'll show some result as well. So this is what we call an unassisted code. It is essentially saying that, well, Alice has the message to be transmitted. She put it through an encoder and then send it through the channel. Now, I have only written one use of the channel here because in the absence of back communication from Bob to Alice, Alice has nothing to wait for. She will finish sending everything in one go. She has nothing to wait for. So I may as well write all n users of the channels she is allowed as a bigger channel n here. Okay. So that's why in this regime, finite block length is sometimes called one shot. And after Bob receives the output from the channel PD code and get his outcome. So that's regular error correcting code, unassisted with nothing. Now, the observation here is that the encoding and decoding operation on Alice and Bob's side, even though they do that kind of independently, Bob has to wait for the channel output to come out, but otherwise it is what we call a bipartite operation. Each of them has an input A and B. Each of them has an output A prime and B prime. And this is a quantum operation completely allowed by quantum mechanics. And this is what the unassisted code looks like. Now, if we wire these inputs and output with the input of the channel and the output of the channel properly, effectively, what it does is that it transforms the original channel N to a new channel in the dash box M. And that's all it does. You transform in channels in a linear fashion. And you always take channel to channel. You will never accidentally take a channel to something that is not a channel. So that's what we are aiming for. We model everything we can do within this restraint. And we call it forward assisted code. So these are just arbitrary bipartite operation. One input from Alice, one input from Bob, the same A and B here, and one output for Alice and one output for Bob. This bipartite operation, somehow I just call it a code. And we wire it the same way as before, as shown in this diagram. And the wiring will only make sense if there's no signaling from Bob to Alice through this box. I haven't said what's in the box. Potentially, it can be very powerful. We'll start to restrict it in a reasonable way in the next few minutes. But the first thing is that we always assume that there's no signaling from this box from Bob to Alice. Otherwise, the wiring will not make sense. Because Alice will not want to wait for Bob to signal to her to do anything in this problem. So it turns out that bipartite operation that does not signal one direction has a very nice structural formula, has first nice structural characterization due to Cherubella, D'Ariano, and Perinotti. And I'll get to that diagram. So if it's non-signaling from Bob to Alice, you can always simulate it with a forward classical channel if you need to. It's not very surprising in one way. Now, it depends on how strong your bipartite operation is. That will determine how much that forward new channel, this forward channel F, is doing. But there is always one channel you can write down mathematically that will allow you to simulate the effect of that bipartite operation. So, and Egling, Schlichman, and Werner call this semi-localizable. So now we want to describe these codes that we want to study. The way we describe it is through the Choi matrix. And I'll describe what it is for the benefit of being self-contained here. So you have a quantum channel. We first consider the one-party case. You have an input, you have an output for the channel. The Choi matrix is simply the density matrix coming out when you apply the channel to half of a maximally entangled state, written here. And we renormalize it with the dimension of the reference system. And we call it the Choi matrix. It's about the same as the Choi state. If I accidentally say one thing instead of the other, you know what I mean. It has very nice mathematical property. For example, if you're given an input to the channel rho, you want to find the channel output n of rho. All you need to do is to plug it into this formula. You take the transpose of the input, times the rate identity, multiply to the Choi matrix, and then take the partial trace of the first index. You promise to get back the channel output. As an example, it has a little bit of interpretation that we teleport that density matrix with never we need to make any correction, and the state will become here. Roughly speaking, that's what it does. So we will always talk about the Choi matrix of the channels and the bipartite operation that we're looking at. So in the case of the forward assisted code that we're looking at, it transformed the Choi matrix of the given channel n to the Choi matrix of the effective channel n in this formula. It looks exactly like the channel output formula. You take the Choi matrix of the input channel, take the transpose, tensor with identity, multiply to the Choi matrix of the bipartite code, the bipartite operation, take the partial trace of the correct system, and you'll get the Choi matrix of the output effective channel. I forgot to define the Choi state of the bipartite operation because I have some trouble manipulating the file. So this is the definition. Again, it is applying the operation on half of a maximally entangled state on the input, and there are two inputs, A and B. So we just write down the maximally entangled state into the input with the reference. Now we relabel the reference as A and B instead of the input AB here. And we give one half of the reference to Alice and one half of the reference to Bob. Because we have two inputs here, when we talk about the Choi matrix, there are two pieces that maximally entangle with the two inputs, and we give one to each of the two parties in the way drawn here. And so this is the object we're studying, the Choi matrix of this code, this bipartite operation. And we want to study the mathematical property of this object. So the first thing is that it has to be a quantum operation bipartite, so it has to be completely positive, which means that the Choi matrix should be positive semi-definite as a matrix. Second, it is trace preserving. You do not lose your state in the process. So in this setting, it means when we trace out the channel output, the reference system should be left in the original state, which is the maximally mixed state with the renormalization. So it is the identity on the reference system. Then we want it to be non-signaling from Bob to Alice so that the code will make sense. Now, in this case, what we'll consider is, what does it even mean? It means that the transformation of Alice input to her output should be independent of what's going on Bob's side. Now, if you look at the Choi matrix for the bipartite operation, it means that if you trace out Bob's output, then you will be able to see that there should be a Choi matrix description from Alice input to Alice output. tensor with the remaining reference state on Bob side. Which means that if we trace out B prime on the Choi matrix on the four system, then we have the Choi matrix of the A to A prime transformation tensor with the identity on B. So that's the non-signaling condition from Bob to Alice. Now, these three conditions we always want. We can now start to impose other conditions that will help us obtain reasonable assistance here. So the first one is we do not allow signaling from Alice to Bob as well. We just exchange Alice and Bob in the equation and obtain a new non-signaling condition there. The second condition constraint we want to impose is what we call PPT preserving. Now, a bipartite quantum state is called PPT, standing for positive under partial transpose. If the density matrix for the state remains a positive semidefinite matrix when you take partial transpose. For example, these are what we call separable state. It's a mixture, probabilistic mixture between completely uncorrelated product state. And if you take the transpose on the first system, it remains clearly a quantum state. So it is still positive semidefinite. Take the density matrix renormalized from the EPR pair. And when you take the partial transpose, you will pick up a -1 eigenvalue in the middle block. And that's usually a signature of having entanglement that you can potentially distill. All we need here is that PPT state does not have entanglement that you can freely distill. And it roughly captures the fact that you do not have a lot of entanglement in the state. It is not equivalent to not having entanglement. But we will not make the distinction in this particular work. Another very nice thing is that the bipartite operation, we call it PPT preserving. If it takes PPT state to PPT state, it does not take PPT state to anything outside, then we call that PPT preserving. Now, it has a very simple characterization in terms of the Choi matrix. It is PPT preserving if and only if the Choi matrix itself is positive, is PPT with respect to transposition of A and A prime. So we have all the constraints ready. We have the three constraints that always should be there. We have the two constraints that we may take one or the other or both. And we treat the Choi matrix of the bipartite operation, this code, as the variable that we want to optimize over. And note that all the constraints are either linear or semi-definite in our variable. So we're in very good shape. If we can find the optimization to be concerning a function, an objective function that is linear also in the variable that we're trying to optimize over. So we choose the fidelity to be this one. We consider sending in half of the maximally entangled state over the input space. So this is k dimension, for example. So we have another k dimension system. Imagine sending through the maximally entangled state, looking at the output after all this coding and the decoding, and ask what is the fidelity of the output state on A and B prime with respect to the maximally entangled state. I use phi to label the density matrix of that. And we just want to optimize the fidelity of this. And it has a very simple form because one of the state is pure. And in fact, using the derivation of what we know, this state the output is just the Choi matrix of the effective channel M here, and plugging everything in, the fidelity has a very simple form, and it's clearly linear in the Choi matrix of Z. So we have all the ingredients to put it together to a semi-definite program. We're given the channel in the form of the Choi matrix. We are given the dimension of the message to be sent, dimension k. We have the variable, which is the Choi matrix of the bipartite operation we are using to do the encoding and the decoding. We maximize this function, the fidelity f, with respect to these three constraints that we always have. We call it a non-signaling code if it is also non-signaling from Alice to Bob, and we call it a PPT code if it is PPT preserving. Before we proceed, let me mention that we can simplify the problem a little bit with symmetry. That if you apply a unitary to half of the maximum entangled state and you undo the output, it does not change the fidelity. So you can apply any U-dagger pair, and you can take the integral over this U-dagger operation over the half measure to simplify the form of the code itself. And it will have the form. Essentially, instead of a Choi matrix over 4 systems, you have 2 smaller operator over 2 systems. And that cut down the number of variables by a lot. Furthermore, if you have symmetry in the channel itself, you can reduce the problem further. That's the numerical data we'll see later. And so now we can start to find results out of these two and compare with previous work. So these are the classes we're looking at. The middle square, the unassisted code, is contained in every other class in this diagram. All the classes I'm drawing, they are convex. So if I put these two pieces together, then I obtain the entanglement assisted class, which does not signal from Alice to Bob. So the entanglement assisted class here is a subset of the non-signaling code, which does not signal either direction. And that itself is, in turn, a subset of the forward assisted code that we saw earlier that does not have back communication from Bob to Alice. Back signaling. It's not back communication, back signaling. I'll skip the forward Hodesky channel here. Now, if you allow two-way classical communication, we are outside of the forward assisted code, and we're down here. And the only overlap, the classical back and forth assistance has in common with the forward assisted code is the unassisted code itself. That's roughly the convention in this diagram. And then the PPT preserving operation by itself does not rule out signaling. In fact, this is modeled. This is used by Eric Rings to model LOCC with arbitrary back and forth classical communication. So it is a superset of the assistants that allow two-way classical communication and has some overlap with the forward assisted code. So these are the classes we're considering. Any questions up to here? Then I can start to compare what we can get here with earlier result. The most popular model to study is entanglement assistance. We have some prior work, but one of the more relevant one is due to Nonsignalling data and Minsoy. They find upper and lower bounds in terms of smooth entropy when you allow entanglement and one use of the channel. The problem is that these bounds, we do not know of an algorithm to evaluate them in general. So that goes to the second step, to try to obtain bounds on how well the fidelity can be, upper and lower bound, using a method that can be evaluated. So one such bound is found by Steph Weiner and Will Matthews, which relate entanglement-assisted codes to hypothesis testing. Now, entanglement assistance turns out to be a rather difficult to model assistance. We do not have exact bound on its performance in the one-shot setting. So what this work does is to relate to hypothesis testing and thereby obtaining an upper bound on the fidelity on the rate distortion trade-off. They were studying classical communication through quantum channel with entanglement assistance. So with the connection, teleportation, and superdense coding, we can turn this problem to communicate quantum data with the fidelity that we want to consider. And therefore, we can start to make a comparison between their work and what we can do with non-signaling code. You can consider the non-signaling code as an upper bound on the entanglement-assisted fidelity. And so we have two different upper bounds from two different techniques. And the question is, how do they compare? It turns out that the code, the semidefinite program derived from the non-signaling code has tighter constraint, despite the fact that we start with a larger class of assistants, which is a little unexpected. But we do not know until we get the final program written down. Furthermore, in the earlier work by Weiner and Matthews, they find that if they take the limit, asymptotic limit when the number of users of the channel is large and when the fidelity is high, they recover the entanglement-assisted quantum capacity. Now, of course, we understand the entanglement-assisted quantum capacity. We know that. But it is a method to check how tight your upper bound is. So they check that, and they find that they recover the capacity itself. So the bound is actually at least tight in that regime. But then if we put these two pieces together, we get one surprise result, that the quantum capacity assisted by non-signaling code is equal to the quantum capacity assisted by entanglement. Because our capacity, our fidelity is lower, potentially. Our capacity cannot be higher. Yet at the same time, it's a larger class, so it cannot be lower either. So the only case is that they're equal. And I think this is not known before. So that's one result that we can show that the two allows you to derive analytic capacity result in some asymptotic regime. Okay. Any question up to here? How much time do I still have? Then the second class of result we want to compare is, sorry about the label, it's not year 2012, it's actually 2001 and 2000 in fact in the archive. I made a mistake there. So we can compare our PPT code, PPT Preserving code, with a very old result by Eric Rings. In fact, the idea to have PPT Preserving code somehow originated from him because he's trying to model LCC. LCC is intractable. So what he did was to model entanglement purification using PPT operation. So roughly speaking, he considered these boxes acting on the two parties, and you input the state that you want to distill. You want to maximize the fidelity of the output bipartite state with respect to the maximum entangled state, subject to the fact that this operation should be PPT preserving. And that's his formalism. And he found a lot of very nice results about entanglement distillation with that framework, both asymptotic and one-shot. I will skip this part about how to make his code for distillation becoming a code that we can transmit quantum data with. But the punchline is that if you have a purification code for the choice state of the channel that we studied, you can turn it to a communication protocol with it within our class. That is PPT preserving. So this inequality holds. Furthermore, if the channel has a form that it can be implemented by one copy of the choice state along with forward classical communication, then we have equality there. So this allows us to say that when we write down the semidefinite program, if we look at PPT preserving code, that is nonsignalling from Bob to Alice, we can identify that result with what Eric Rings has already done. Then we can start to ask if we also add the non-signaling condition, do we gain beyond what Eric Rings have found? Okay, so that's the question we're asking. So this is one example of the actual data. This is the qubit deploying channel, which, as mentioned earlier, it takes the qubit state to itself with probability 1 minus eta. Sorry about this, it's eta multiplied to the maximum mixed state on the qubit. We take 5 copies of it just because the smallest one error correcting code for encoding 1 qubit has block length 5. So we again consider sending a 2-dimensional state, which means that we encode 1 qubit in 5, and check what's the best fidelity under these 3 classes of codes. And we find that, yes, if you add the non-signaling constraint, you get tighter bound, lower fidelity relative to the unassisted case. We hope to find an asymptotic result in this because the asymptotic capacity of unassisted capacity of the deploying channel is a wide open problem. We just need to we need a little time, maybe some dedicated student to extend the result by finding a good dual solution. Let me mention another thing up front. A very attractive reason for us to look at semidefinite program is that if you find a feasible solution for the dual program, you can already have an upper bound to your original problem. And so if we can manage to guess a form of the feasible dual solution for the asymptotic case, we can potentially find upper bound on when we can find upper bound on the fidelity asymptotically, and hopefully that will give us a limit on when the capacity can fall to 0 in the deploying channel case. We're still working on this, and a lot of what I mentioned makes very good student project as well. You can make a student do the code and so on. So let me just advertise it further. I really hope that more people can use this code that we have developed. The second example we look at is the QuICS whole-level Werner channel. So this dense matrix here is 3-dimensional, and this is just how the channel works. But I'll say more easily. This channel has Troy matrix, which is the projection onto the antisymmetric space between 2 3-dimensional systems. This is what the channel is. There are a lot of interesting properties about this channel. It has no quantum capacity because of symmetry. Due to some result by Wen Yao during Simoni, Zaffaroni, and Andreas Winter. This channel has no zero error quantum capacity, even with free entanglement for free. However, if you allow some vanishing amount of error, it has entanglement assisted quantum capacity half times log 3, which we have just shown that it is the same as a non-signaling assisted capacity. The PPT assisted capacity you can read off from Ring's work, that is log 5/3. And if you're curious, log 5/3 is smaller than half log 3. So now let's run the finite block length analysis. We fix the number of channel users to be 2 here in this plot, vary the dimension of the state we want to send through, and plot the exact fidelity optimized over these 3 classes. The first thing to notice is that the non-signaling and the PPT preserving bounds are incomparable. Sometimes one is better than the other. And when you put both constraints together, you do better than the min of the 2 upper bounds. So we do see some value in the framework. And the second thing to notice is that I wonder if any one of you see that this looks like 1 here with fidelity. It is actually not just numerical, but analytically, you can show that the fidelity is 1, which is intriguing because even with free entanglement, this channel has no zero error quantum capacity. We're a little surprised by that. But to be fair, let's look at the Venn diagram here. This is entanglement assistance, and this is PPT and non-signaling assistance here. So the 2 are somewhat incomparable. We shouldn't be too surprised, but it is somewhat surprising to us that we can achieve zero error communication from a channel that has no capacity by itself, has no zero error capacity with free entanglement. We're very curious about what this is. We do not know that it is super activation, which would mean that we can rewrite that by Patat operation as if you use forward entanglement binding channel. For those who are interested in this problem, you can talk to me offline. And likewise, we can run the program a little differently. We can fix a rate. We pick 2 here. And then we can increase the number of users and pick the size of the message to go roughly 2 times the number of channel used with a rate R. Small r is the same as big R on this slide. And we focus on the most restricting set of assistants here. And we check 2 rates that are very close to the PPT preserving capacity, preserving code capacity. But we subtract different amount until we see a dichotomy here. In one case, when the rate is sufficiently low, it will converge to, it looks like numerically it's converging to 1 as n goes to larger and larger value. In the other case, it looks like it's decaying exponentially. So we have a conjecture that for this particular channel, the PPT and non-signaling assisted capacity is strictly smaller than log 5/3. And once again, it would take a little work to find the correct dual feasible solution to prove that analytically. So there are a lot of open problems. As mentioned earlier, we want to find asymptotic capacity result using this framework. And the original problem I mentioned about the 3-qubit amplitude-damping code is unresolved. After we run the program, we still see the curve going down as if it may have an error correcting code in that class. So we do not know whether there is an unassisted code that will correct for one amplitude damping error or not. My personal take is that there is none. I actually think that there's none, and I want to prove that it doesn't exist. So one possibility is to strengthen the PPT constraint to say something that looks a little more like a separable operation that may put us to have to consider cone programming instead of semidefinite programming. It's doable if you have a very good student. The alternative is to consider, instead of the PPT constraint, we can have a family of semidefinite programming that will converge to the separable class. So both of these are doable in some way, as long as we have enough time and energy to sit down to do it. And I'm very curious because I do want to find out if I can have, after all this improvement, maybe I can rule out the 3-qubit amplitude damping code. Or if I put this in, it still exists, maybe there is one, and I can start to look for one using the hint. When you run this semidefinite program, you actually get the variable as an output to the program as well. So you know what the code is like. It's very attractive procedure. And then, okay, I have time to discuss that open problem. So let me get back to this characterization here. This code always has a description that you can always model it by allowing a forward side channel of various strength. It will be true if it is a noiseless channel. If it is a totally garbage channel, you have no assistance there. But one thing you can consider in this side channel is what we call forward Hordesky channel. It is sometimes called entanglement binding channel. It is a channel that cannot be used to create state that is not positive, that is not PPT. Once again, the characterization is that the channel of this type have Choi matrix that is positive, have positive transpose. We wonder if the code that we have for the QuiCS level channel has an implementation in terms of a forward entanglement binding channel or not. If we do, then we'll obtain a very strong superactivation result that we put a PPT channel together with the QuiCS level channel that has very, very little capacity in many, many forms. And put two things together, then we can send 1 qubit error-free completely. But we do not know. Let me mention on the side, I have no slide prepared here, that these classes, that is non-signaling both way, and PPT preserving can nonetheless require some noiseless forward causal communication to simulate in some examples. We have examples that require that, but it is not always needed. So we do not understand what it takes in terms of this forward communication to implement a particular code of this form. That's another open problem. We would like to know a little more. So I think that concludes my talk. Thank you very much for your attention.
Comments?
Maybe it's a silly question, but so you consider this maximally entangled state to define your fidelity? Is this the most general thing one could consider, or could one consider, you know, over the worst possible fidelity over all possible inputs? Or
thanks for asking that question. I should get you a drink because I forgot to mention it. It is related to the average. So if you only consider pure state input, and you want to maximize, you want to consider the average case input-output overlap fidelity, the two fidelity are related by a very simple constant factor like 2/3 or something. But it is not the same as some other measure like the diamond norm. How close is your transmission to the noiseless channel? We do not capture that in that. We call it entanglement fidelity. We cannot capture the diamond norm with that fidelity. We use it mostly because it gives very good mathematical result and is very reasonable in a lot of settings. But it does not have the diamond norm flavor, and therefore we do not know of how well it composes with other procedures.
Maybe I have a question. In the open problems, you mentioned that we can improve. Maybe we can improve PPT constraints to the SAP or the KE extendability. And we know that for the 2E extendability, it corresponds to the anti-divisible channel. Mm-hmm. And I'm just wondering for the general K, what the channel looks like.
Can you say that last sentence again?
Oh, I mean, for the case K equals 2, the 2E extendability just correspond to the anti-divisible channel.
Right.
And I'm just wondering for arbitrary K, the channel something like the broadcasting or.
I think the structure of the two extendable case is still a little. It is probably related to the broadcast channel, but it is not so well understood in the form like, say, when you have degradable or anti-degradable channel on a qubit. We know a lot about it, but we do not know quite as much in larger dimension.
I see.
So even there, it is not very clear how to proceed. I do not see any real obstacle to actually do it, but it is not something that we can just do
I see.
as a part of the paper, because it is really a separate job to write down what it means and write down the program and so on.
Yeah. Okay, let's thank Debbie again.